All right, guys. Up there, roughly sketched are two pair functions, sine and cosine. Okay? Now, what I want to ask you is, how far do I need to move the cosine? And it's essentially move that point to become that point. How far do I need to move that to the right so that the cosine lands on top of the sine? Pi over 2. Okay? So what we can do is say that the sine function would be the same thing as the cosine moved to the right pi over 2 units, right? Okay. Now, what I want us to kind of realize here is the relationship between sine and cosine and the relationship that is built in their names. If I look at the sine and the cosine, they're very similar, correct? What's that co stand for? I think we've talked about this before. Complementary, okay? Which geometrically means add to 90 degrees, right? Or in radians, pi over 2. Meaning that if I take, let's just do it in degrees, the sine of 30 has got to be equal to the cosine of 60, correct? And if we type those things on a calculator, it will say 1/2 is equal to 1/2. But in this situation right here, you can obviously see that 30 and 60 are complementary, right? Okay? So my arguments, when we say sine and cosine, the arguments are always complementary. Add those two things together, what do you get? Add x and x minus pi over 2. Do you? You should, but does x plus x minus pi over 2 give you 90? Because it gives you 2x minus pi over 2, doesn't it? And that's not 90. So let's do some algebra here to see if we can make that realization that it does indeed give us 90. Okay? So, in order to do this, and this gives you a snapshot of all the properties that are useful in trig that can allow us to transform the way something looks. Okay? Do you guys remember these properties? One, they were called the even-odd properties. And basically they said that the sine of negative x is the same thing as the opposite of the sine of positive x. And that's simply because of the symmetry of the unit circle. Okay? And then we had another one that said, dealing with cosine, was that the cosine of negative x is the same thing as the cosine of x. And basically what that means is it's easier to show on the cosine. If I go cosine of negative x on the unit circle, so that's negative x right there. Well, isn't that the same value as going positive x? Because the cosine, remember, the cosine is simply the distance it takes to get in the x direction to either one of those points. Well, if I go negative x, it's the same distance as going to positive x, right? Does that make sense, everybody? Okay. Similar relationship over here, but we have to negate something. We have to negate the sign of positive x to do that. Okay, because, well, I'll just draw it. Over here, if I go negative x for the sine, so that's negative x. So the y value down here, y value would be negative down here, right? Okay. Well, if I want to go positive x, which would be this y value, what's the y value up here? Y value is positive. Okay. How do I make that y value and that y value the same thing then? If one's positive, one's negative, I need to multiply the one up here. I could do it to either side, but it makes more sense to do it to this side. I multiply that one up there by negative, and it will make these two y values equal then, right? Okay? Those are even odd properties because we have symmetry in the unit circle. These properties then are going to be the tool that we use to rewrite this. Okay, so I'm going to start with that. I'm going to say sine of x equals the cosine of x minus pi over 2. Okay, and I'm going to manipulate the right-hand side. Okay, and this is, as you work through algebra courses, you learn this type of manipulation or these possibilities. It's not all that obvious, okay? But what I'm going to do is I'm going to factor a negative out of this positive x. If I take a positive x and factor out a negative, factoring out is the same as dividing, right? So we'll take this x and divide it by negative 1. What will that leave that x as? If I take positive x and divide it by negative 1, it turns it into what? Negative x, doesn't it? Okay. Now, if I factor it out here, I got to factor it out here. It's more obvious factoring a negative out of a negative number. It's going to leave me a positive number, right? That argument is still identical to this argument here. 100%. Factor or FOIL that, not FOIL, distribute that negative back through. Negative times a negative x, positive x. Negative times pi over 2, negative pi over 2. They are identical, correct? And we'll demonstrate that here in a moment as well using a graphing tool. But now, what I'm going to look at is this here. Okay, and I'm just going to call that an object. Okay? It might be just x. It might be a singular thing, but it might be a quantity. Could be another function. Okay? And in our last statement that we wrote, this here is this stuff here. Does that kind of make sense? Okay. If you want to make it real obvious, we could do this. We've played this game before. We could say, let u equal negative x plus pi over 2. And now I can rewrite this as cosine this negative. And now this thing I just said, let be u, it would look like that, right? Does that make sense? Okay. And now it might be more obvious how to use this property. Cosine of negative x or cosine of negative u turns into cosine of x, or in this case, just cosine of u. Let's bring u back in, which was negative x plus pi over 2. Now, for whatever reason, textbooks won't leave it that way. They'll use a commutative property, and then we'll rewrite this as cosine of pi over 2 minus x, which in that orientation, it is not easy to see the direction that we had the transformation take place. Here, right there, we knew it was a transformation to the right. We had a phase shift of pi over 2 units to the right. Okay? That is not as easy to see down here, but it is still true. Okay? And we could even maybe start arguing that it's actually a phase shift to the left of pi over 2 and a y-axis reflection because of where that negative is, okay, on the x. Okay, but and moving left and right, I think it's easier to see this way. Now, okay, so if I bring my sine of x down here, now take these arguments. What's x plus pi over 2 minus x? Is it pi over 2? X is cancel, right? Pi over 2, same thing as 90 degrees. Now do we see the co-function relationship between those arguments? Okay. So that's the way a lot of textbooks are going to present to you the relationship between sine and cosine as horizontal shifts of one another. Okay. But it's not, the reason I show this is because it's not as obvious as what you may think. Okay. You may think that, oh, it's x minus pi over 2. And that's fine. You want to think about it this way. I think about it that way most of the time, okay? But there may be applications where you see this and it throws you for or it throws a curveball at you, and you just got to pay attention to this idea. Is that okay? And we can, as we go through this kind of stuff, and you're worrying about your properties and applying movements to things, okay? So we know sine of x, okay, should equal cosine of x minus pi over 2. Just want to see if those two things equate. So they do equate, because I can see that they are graphed on top of each other there, right? Okay. Then we rewrote that as the cosine of negative x plus pi over 2. And I want to know, is that okay? Well, toggle back and forth. It is the same as what was written above, right? And then I want to know, okay, well, if I let essentially that negative disappear, I get that. And that's the same thing. Okay? And then commutative property says pi over 2 minus x is maybe a better way for us to write it. And we see that that does indeed lay on top of the sine of x. So we can go all the way from sine of x to cosine of pi over 2 minus x. And all these intermediate transformations or adjustments to our function can be shown to be valid because they lay on top of what we started with. Does that make sense? Okay. We could do the same thing with the secant and the cosecant. Do the same thing with tangent and cotangent as well. Usually you're going to see, for us to be able to use these properties the best way and to see that relationship, they're usually going to start you off with, let's say, if we take the secant function, let's just graph this real quick. We all secant of x and cosecant of x. Do we see that if we take the blue one and move it pi over 2 units this direction, so add pi over 2 units, it's going to become the red one? Okay. So I'm going to take so if I start with secant of x equals cosecant of x. Now they don't equal the same. I need to take the blue one and move it pi over 2 units to the left. Okay? When we do that, it's not, I don't particularly care for this relationship. If I go through this using the same kind of structure we just did, I take a negative out of here. Okay. Now the cosecant is going to have the same even odd properties that the sine had, because the cosecant and sine are reciprocal. So the sine said the sine of negative x is equal to the opposite of sine of x. So the cosecant of negative x is going to equal the opposite of cosecant of positive x. So basically what's going to happen is that negative right there is going to be brought out front, negative cosecant of negative x minus pi over 2. And then that's real. I mean, we can kind of get stuck there with our problem. We could take another negative out. Think about this. If I have this negative there, take another negative out, so a negative, and this will turn back into a positive x. This will turn back into a positive pi over 2. And we're back to using this property again. That negative come out front. And I get back to cosecant of x plus pi over 2, which is exactly what we started with, right? So it's kind of a cyclical relationship. Basically what happens is that if I use the cosecant, if I shift the cosecant to become the secant, I don't necessarily right away get the connection that the arguments are complementary. Okay? But if we do it the other way, let's say we start with the cosecant, and let's move the secant. So if I start with the blue one, okay, I need to make it become the secant by, sorry, let's start with the secant. Move the secant. Well, how far do I need to make the secant move to become the blue one? Pi over 2 again, right? Okay. So that one needs to be moved pi over 2 units to the right. Okay. So it will be minus pi over 2, right? So secant minus pi over 2. Okay. And again, now with this one, you don't necessarily see that when I add the arguments together that I get pi over 2 or I get 90. So the secant has the same relationship that the cosine had with even odd properties. So if I go cosecant of x is equal to secant, okay, now I can take a negative out of these, so it'll be negative x plus pi over 2, and now that negative, which would be correlated to that one right there in the property, will vanish when I rewrite it. So this is equal to secant then of negative x plus pi over 2, and we get secant of pi over 2 minus x. And that is a lot of times the way, like your cotangent functions, or not, sorry, not cotangent, cofunctions, secant and cosecant, sine and cosine, how they're going to be described to you. They'll be described as cosecant is equal to the secant of pi over 2 minus x, and then the sine is the same as the cosine of pi over 2 minus x. That's usually how a textbook, if we actually utilized a traditional textbook, we could find that written there. But you'll never see it written that the secant, like I did here, the secant is equal to the opposite of the cosecant of the opposite of x plus pi over 2. It's true. We could graph that, and they're going to be the same. But this is, do you guys agree in complexity that this is messy? And it is a lot messier than this, which says the exact same thing. It provides the exact same relationship. So they provide that one instead. Is that okay with everyone? Okay. So just wanted to make sure that we see the relationship between those co-function functions. They're named the way they are purposefully. Okay. I think last week we talked similar thing about the tangent and the cotangent. What I would like to do right now is go through, and basically what we're going to do over the next day and a half, we're going to graph, I think, 2 more of these transformations today. We might start class tomorrow with 1, but then I would like to, tomorrow in class, get to the inverse functions and how we graph those, because then those will be ultimately 6 more parent functions that we can move around left, right, up, down, that kind of stuff. Okay. But my hope is that the transformation procedures are already learned. Okay, from college algebra. We were successful in college algebra. My hope is that that information has stayed with us. There's a few caveats that we need to adjust for in the trig aspect of things. For instance, we need to talk about the period and all that kind of stuff, which we did not talk about in college algebra. Whenever you do a transformation, whenever you graph really any trig function, first thing you need to decide is what is the period. And the period for the tangent, anybody remember the period for the tangent? Period is pi, okay? And it's going to be, it's always over b, okay? So if it's just a parent function tangent of 1x, 1 is your b, so it should be pi. In this case, b is what value? It is 2. Okay, it's that value right there. Now the way that this function is written is in the convenient format, because they could have provided it as y equals tangent of 2x minus pi over 2. Just remember that when we want to do horizontal movements, it is best to have the x variable with a coefficient of 1. So we factor that out, and this is the way they presented this one. Okay, but they could have just as easily presented the same exact graph that way. Okay, so we got our period. What I'm going to do real quick is just graph, just so it's a tool for me to transform eventually. I'm going to graph tangent of x. Okay, so just going from memory here. If the period of tangent is pi, then we'll have an asymptote at pi over 2 and an asymptote at negative pi over 2. And that's because of the unit circle. Sine divided by cosine at pi over 2, negative pi over 2 is an undefined quotient. At 0, we have 0 divided by 1 for the sine divided by cosine. So that gives me a y value of 0. At pi over 4, we get root 2 over 2 divided by root 2 over 2. So it gives me a y value of 1. And at negative pi over 4, it's negative root 2 over 2 divided by root 2 over 2. So it gives me that. So there are the 5 components that we're going to use to graph our tangent function. Okay? The one thing to remember, and it's really hard doing this by hand, especially with a scale, may have some human error in it. The curve that connects those is somewhat like an inverted S, or some people say it looks cubic. Just kind of keep that in mind as we do this. It's not a straight line through those 3 points. It's kind of something like that. So that's always in the back of my head. It's always in my mind when I'm graphing transformations. Whether I draw it down in front of me, which I think in your guys' experience, you've been doing this for maybe a week now, it probably makes sense to draw that every single time. The more you draw that, the quicker you're going to just kind of embed that in your memory. The quicker you're going to be able to ultimately, eventually, not even have to write it. Okay? So we're going to do the same thing then, but transform it. So now the period is now going to be pi over 2. Okay? Well, the period on the tangent is ultimately the distance between the two asymptotes. Okay? When we shrink things, that's what's happening here. We're having a horizontal compression. You're essentially pushing that asymptote in, and you're pushing that asymptote in to pi over 4 increment. Okay? So if I put pi over 4 there, and negative pi over 4 there. Okay? It is of utmost importance to label your x-axis. If I don't put labels on my x-axis, then the graph means nothing. Okay? Does that make sense? Because if I forget to put a label there and I let the reader interpret, well, okay, that's a 1. Well, that would be a completely different function that I'm graphing if that pi over 4 is actually a value of 1. Okay? So just be aware of labeling. It's very important. So is that distance between those? Is that pi over 2? Just like the period that we wanted, right? Okay. Our asymptotes are going to exist there. So we're drawing my asymptotes. And then once I have those, it's just looking at these 3 points from the parent function and applying the relationship that we got on the parent function and how they were developed on that relationship down here. So what I mean by that is that, would you guys agree that in that region right there that is yellow, that point that I need to plot is halfway between that region? So that yellow region on the transform function correlates to that. So my value, my point right here, my coordinates need to be halfway here, which that would be pi over 8. And the y value is 1. That point right there, still going to be 0, 0. And now this blue region correlates to this blue region. Halfway in between. So at negative pi over 8, we reach a height of negative 1. Okay? So, all we did there was we adjusted the period so far, right? That's all that happened. Took our normal period between negative pi over 2 and pi over 2, and we squeezed it down from both sides, and everything kind of folds in or slides in, kind of an accordion-like thing. All these points push in. So a point that was here normally, a point that was here normally, asymptotes that were there and there normally, we push it all in, and it compresses to these 3 points and these 2 asymptotes. Is that okay? Now, so basically what we have right now is y equals tangent of 2x. That's all we have right now. What does this tell us we need to do? Where's that going to move things? To the right, pi over 4 units, right? So I'm going to label my x-axis appropriately for that. Now, what's nice is whenever you have a denominator in your phase shift, you're going to want your x-axis either to be written in that denominator, which we have, so that's good, or in a multiple of that denominator. So if my x-axis was written in 8ths or 12ths or 16ths or anything like that, that would be useful. Does that make sense? If my denominator is written in thirds, we're going to have to spend some time. It's doable, but we'll have to spend some time breaking things down. And essentially, if my denominator was force right there in the problem, and I had, for whatever reason, my x-axis written in thirds, basically what I would do is try to rewrite my denominator, or rewrite my x-axis and my denominator in 12ths to make the transformation easier. Okay? Because basically what I want to do is write my x-axis so that I can just count how many tick marks each point needs to be moved over. And if it's not all consistent, using multiples of that denominator, it's not going to be very easy. You're going to be guessing a lot. Okay? So I'm going to take that yellow distance. So that's pi over 4. So this would be 2 pi over 4. Oh, yeah, 2 pi over 4. This is pi over 8, 2 pi over 8. That point would be 3 pi over 8, right? Okay? And what's going to happen is that every single feature up there needs to be moved pi over 4 units. Well, the way I've established this is that this yellow region is made up of 2 tick marks. So 2 tick marks represents pi over 4, right? So does it make sense that this point here needs to move 2 tick marks? And it's going to go right there. Does that make sense? Every other point is going to move the same way. 2 tick marks. 2 tick marks. So I move the points. Asymptotes are also features that need to move. So that asymptote is going to go 2 tick marks to the right. This asymptote is going to go 2 tick marks to the right to come the y-axis. Okay. And I'm just going to highlight here the final information. We'll do this in pink here. That should be an asymptote. That should be an asymptote. Point, point, point. And we want a smooth curve through it. Now, every one of your graphs may be different because you might have gone out a little bit further to define where your pi over 4 was than what your neighbor did, right? Okay, so I could not, if I left it all up to you, gave you all the freedom in the world to graph this, and I collected those, there's no singular transparencies that's going to graph every single one of them. So what I'll be looking for, if I were to do that, what I'm looking for would be that ordered pair. Pi over 8, comma 1. That ordered pair. 3 pi over 8, comma 1. This would be a negative one there. I'd be looking at pi over 4, comma 0. Asymptote at x equals pi over 2. Asymptote at x equals 0. If I can find those features, then I know everybody's done it correctly, right? And what I like to do, if I'm practicing these on my own, is I go and put those features in. We had an asymptote at 0, so x equals 0, x equals pi over 2 is another one. We had the point pi over 8, pi over 8, comma, negative 1. We had pi over 4, comma, 0, and we had 3 pi over 8, comma, positive 1. We had those 5 features, right? I can't hear a thing you said. This 2 here, that 2 is a horizontal. That 2 impacts the period, which is the x-axis. If I want a vertical stretch, the 2 would have to be out here. Say it again. Not sure. Like, do I want that point right there? Yes. Yes. Yeah. Because that's one of your parent function points. Because otherwise, so the argument would be, do I need just that one in the asymptotes? I would want those extra 2. If we graph these then, okay, so those are the 3 points. So now I'm just going to ask Desmos, can it graph the exact function that I started with? Tangent of 2 times x minus pi over 4, and does the graph pass through the 3 points that we found, and does it abide by the 2 asymptotes that we established? And it does. So I'm guaranteed that I have here, well, get there. Here we have the 1 period of tangent of 2 times quantity x minus pi over 4. Okay? Just be cautious, because there will be times where they write tangent of 2x minus pi over 2. And it's the same thing. Okay, so this one they factor the 2 out. This one the 2 is in there. All right. That kind of makes sense? Yes. They might. So if we want more than 1 period on this, because a lot of times on like tests that have been written by Rhodes that now this year all tests are my freedom to write. But they might say graph between 0 and 2 pi. So basically what I would have to do then is take this thing and just through cutting and pasting, basically paste it again. And now that would be 0 to pi, right? And then I would need to take it and do 2 more pastings. But the idea there is that if you've already got this initial period constructed with the x-axis and y-axis labeled, then it's just adding basically pi to, so this point here would be 9 pi over 8, right? Just add 8 pi to 8 pi over 8. So I can relabel my x-axis just by adding pi to these previous intervals. Let's jump. We got time to do one of these with cosecant. The approach with cosecant and secant are a little bit different than what we've done so far, because with everything so far we have done the direct use of parent function points. Okay, the one we just did was the use of, the asymptotes being at pi over 2 and negative pi over 2, y values of 1 when we're at pi over 4, negative pi over 4. So those are parent function points for the tangent. We don't do that with secant and cosecant, at least not directly. What we end up doing is actually never graphing or dealing directly with the cosecant. And for whatever reason, none of my mice work. What's going on here? No. Okay. There we go. All right, so you see I've already gotten some of this stuff written in here. Let's erase that and go from scratch. If we look at the cosecant, 1/2 cosecant of 2x, first thing I want to do is make the relationship that cosecant is the reciprocal of what? Sine. So I'm not going to graph this. I'm going to replace that with sine. I'm going to graph 1/2 sine of 2x. Okay? Well, pay attention to the period. Period is 2 pi over what? So over b, in this case, b is 2. So the period, so when I graph the sine function here, I'm only going to go out to pi. Okay? But the sine function, doesn't that get cut in half? And then in fourths, right? Is it okay establishing the x-axis for this? That way. The sine function goes between what two numbers on the y values? 1 and -1. Okay? So the way I establish my x-axis right now is taking care of that too. What's this 1/2 going to do to each of the y values on the parent function of my sine curve? Normally, so if I just had sine of 2x, I would normally be at a height of 1, right? It's going to cut it in half. So it's going to make that height go to 1/2. Okay? This is going to get cut in half, and this is going to be a height of -1/2. And when I graph that, okay, so we squeeze the period down, but the symmetry of the sine function, no matter what the period is, still exists. So it's going to have x-intercepts at the beginning and the end. It's going to have x-intercept halfway in between. It's going to have maximums and minimums at the quarter points. Okay? That right there is the graph of 1/2 sine of 2x. That's not what we wanted, though. The original problem said cosecant, right? So this is where we bring in the cosecant relationship. Cosecant has asymptotes at the sine's what? X-intercepts. So 1/2 cosecant of 2x is going to have x-intercepts at 1/2 sine of 2x's, or so it's going to have asymptotes at 1/2 sine of 2x's x-intercepts. Does that make sense? So asymptote there, asymptote there. This point here is a maximum on 1/2 sine of 2x. it becomes a what on 1/2 cosecant of 2x. Becomes a minimum. Okay? And this is where yesterday I said, really the asymptotes in that point are the only thing that we're going to be interested in, because to find those other points, it's kind of difficult. Okay? And if we understand how we should behave around asymptotes, this gives us a good enough understanding of what the graph should look like. That minimum on the sine function becomes a what on the cosecant? Becomes a maximum. And now, if I go to Desmos and I graph x equals 0, x equals pi over 2, x equals pi, and get those asymptotes, and then graph the point pi over 4, comma 1/2, and 3 pi over 4, comma negative 1/2, okay, and get those two maximums and minimums, plot those, and then go to the next box and type in 1/2 cosecant of 2x, that curve will fit through those features that we just established. Does that make sense? So the cosecant, you don't really graph the cosecant until the last step, right? Does that make sense? Replace cosecant with sine. So if I was going to ask you to graph the secant, what would you actually do instead? Graph the cosine. Okay? You only do that with those two. You would not do that with cotangent. Cotangent, you have to use the parent functions for cotangent, or parent points for cotangent. It's not as easy to use the tangent function to graph the cotangent. You can, but it's not easy. There's an assignment on 6-4. I got to open till Friday, I believe. My plan for tomorrow, I think I already said this, though. I want to start with, we'll probably start with this one, but I'll change it to secant, because we've already done a cosecant one. And then transition into dealing with the inverse functions. Okay? Once we get through inverse functions, then we can start talking about how we're actually going to use this stuff in problems. Okay? We want to start solving equations. Okay? And we're kind of building to that first technique of ever solving any equation is always a graphical approach. In order to apply a graphical approach, I need to be able to graph. So that's what we're working on.